So in previous lecture, we started discussion on iron carbide phase diagram. We discussed the different phases present in iron carbide phase diagram. So cementite. So this photograph is of pearlite, of 100% pearlite, and we can see here alternate layers of ferrite and cementite. So we'll discuss more about different phases present in iron carbon diagram, how these phases are formed during solidification, during heat treatment processes. That all will study in phase transformation model. So body-centered cubic structure. So you can see here ferrite. It is a body-centered cubic structure. It is a soft and ductile, and maximum solubility of carbon in ferrite is about 0.025, and that is at 727 degrees centigrade. So means ferrite is an interstitial type solid solution. Obviously, it is a present at one of the terminal of the phase diagram. So we call it is a terminal solid solution. So as you can see it here, so these spheres, so these are Fe atoms and these are carbon atoms. So you can see here carbon atom. So this is the position of the carbon atom present in a body-centered cubic structure, and these are all octahedral sites, whereas this site is a tetrahedral site. So means the carbon is present in a tetrahedral site in case of body-centered cubic structure. You can see it here also. So this is the position of carbon atom in case of body-centered cubic structure. In case of face-centered cubic structure, again we have two sites, octahedral sites and tetrahedral site. The maximum solubility of carbon here is about 2%, that is at 1147 degrees centigrade. And as you can see here, location of carbon present in case of face-centered cubic structure, and this site we call octahedral site. So interstitial sites. So in case of face-centered cubic structure, we have two interstitial sites where carbon can fit, and these two sites we call interstitial octahedral site and tetrahedral site. So site radius in case of face-centered cubic structure of octahedral site is 0.052, and is of tetrahedral site is 0.028 nanometer. In case of body-centered cubic structure, octahedral site radius is 0.019 and tetrahedral site radius is 0.036. As you can see, the radius of carbon atom is 0.08 nanometer. So in case of FCC, it occupies octahedral site because 0.052 and 0.028. So 0.052 space is sufficient. So it occupies octahedral site in case of FCC atom. So small distortion is present in case of octahedral site. System is always looking for lower energy. So it prefers octahedral site because it is 0.052. And in case of BCC, you can see octahedral site radius 0.019, tetrahedral site radius 0.036. So surprisingly, it occupies the octahedral site in BCC, not the tetrahedral site, despite the smaller size of this site. As you can see, octahedral site is 0.019 and tetrahedral 0.36. It has to take tetrahedral site, but it will not take tetrahedral site. It will take octahedral site in case of body-centered cubic structure. Why it prefers octahedral site compared to tetrahedral site in case of body-centered cubic structure is due to the presumably because of the low modulus along 100 direction. It prefers octahedral site radius. So let us start discussion about the phase transformations. The phase transformation, change of the microstructure can be divided into two categories. So congruent transformations and non-congruent transformations. So congruent transformations means with no change in phase composition or number of phases present. For example, melting, solidification of pure metal, allotropic transformations, recrystallization. Here there is no phase composition or number of phases will change. And second type of transformation is non-congruent transformations with changes in phase composition or number of phases, eutectoid type transformations. Here, phase composition and number of phases can be changed. So we'll discuss these phase transformations in this particular sessions. So first of all, we will discuss non-congruent transformations. So non-congruent transformations, as we already discussed in previous lecture, there is a change in chemistry and there is a change in number of phases present due to this kind of transformations. So non-congruent transformations, the first transformation is peritectic transformation, where it is at high temperature transformation, where liquid plus delta transforms into gamma. In eutectic transformation, again it is a liquid to solid transformation, where liquid transforms into two different solids, gamma and cementite. And eutectoid type transformation, so this is a solid to solid transformation. So solid 1 transforms into two different solids, solid 2 and solid 3. So solid 2 is alpha and solid 3 is a cementite. So this is a eutectoid type transformation. So you can see here, so 3 spots indicates invariant points. So the first is blue color spot here, that is at 0.08% carbon and 723 degrees centigrade. So this we call eutectoid point. The composition corresponding to this point we call eutectoid composition, that is 0.8% carbon. And composition corresponding to this point, temperature corresponding to this point is 723 or 727 degrees centigrade, we call eutectoid temperature. Similarly here, you can see, so this is a eutectic point. So temperature corresponding to this point we call eutectic temperature, that is 1147 or 1148 degrees centigrade. And composition corresponding to this point, that is 4.3% carbon, we call eutectic composition. And similarly here at the peritectic point. So development of microstructure, how microstructures are developed in case of steels. Now as you can see it here, for solid to solid transformations, we are not considering eutectic point and peritectic point. So we'll look at this only the small portion of the phase diagram. We just consider the small portion of the phase diagram, which is very, very important as far as our heat treatment transformations are concerned. Because most of the heat treatment transformations or all heat treatment transformations are solid to solid transformation, where one solid transforms into two different solids. Now this point you can see, so this point composition corresponding to this point is 0.8 or 0.76% carbon, we call it eutectoid composition. And temperature corresponding to this point we call eutectoid temperature, that is 727 degrees centigrade. So the steels less than 0.8% carbon we call hypoeutectoid steel, and steels containing carbon greater than 0.8 to 2% we call hypereutectoid steels. And the steel which contains exactly 0.8% carbon or 0.76% carbon we call eutectoid type steels. So three categories of steels are, we have done the three categories of steels based on their chemical composition. The first category is hypoeutectoid steel, contains less than 0.8% carbon. A eutectoid steel exactly contains 0.8% carbon, and hypereutectoid steel contains more than 0.8% carbon up to 2%. Beyond 2%, cast iron starts. So we have categorized the steel based on its chemical composition. So the microstructure also you can see here how the microstructures are developed. As you can see, so this is the microstructure of a eutectoid steel. which contains 100% pearlite. Then microstructure of hypoeutectoid steel, it contains ferrite plus pearlite. And microstructure of hypereutectoid steel, which contains cementite plus pearlite. So again, carefully look at the slides, it is very important. Eutectoid steel contains 100% pearlite. Hypoeutectoid steel, it is a mixture of ferrite plus pearlite. Hypereutectoid steel, it is a mixture of cementite plus pearlite. So as percentage of carbon from 0.022 percentage, starting from 0.022 percentage, increases up to 0.8 percentage of pearlite gets increases. And beyond 0.8 percentage of pearlite decreases. So means exactly at eutectoid point we have 100% pearlite, and that can be determined by using lever rule that we already discussed. If you want to find out the percentage of pearlite and ferrite present at suppose 0.4 percentage carbon, find out percentage of pearlite present at 0.4% carbon at room temperature. So this is the exercise for you. You just solve it and find out the percentage of pearlite present at 0.4 percentage carbon. Similarly, find out percentage of all the phases present at 0.52 percentage carbon at room temperature. All the phases means ferrite, pearlite and cementite. So the pearlite is a mixture of cementite plus ferrite. So that's why we see there alternate layers of cementite, ferrite and cementite, ferrite. So how the pearlite forms, how ferrite forms and how cementite forms. So that we will discuss in phase transformation. So here we'll try to understand how phases forms. So the maximum solubility of carbon in gamma ion is 2.11% carbon or 2.04% carbon. And eutectic point, composition corresponding to eutectic point is 4.3. So what is the eutectic reaction? It says liquid transforms into gamma plus cementite. So this is our eutectic reaction. Liquid transforms into gamma plus cementite. So liquid, solid 1, solid 2. If you want to write generalized form of the eutectic reaction, you can write it as liquid transforms into solid 1 plus solid 2. And if you want to write this eutectic transformation for iron carbon phase diagram, then you can write it as gamma plus cementite. Similarly, point B, it is a eutectoid point. And eutectoid point, for eutectoid, parent phase is a gamma, that is austenite. So austenite transforms into two different solids, alpha plus cementite. The generalized form will be solid 1 transforms into solid 2 plus solid 3. As you can see it here, initially we have only austenite region. So obviously we have only one phase austenite. As we know, austenite is a interstitial type solid solution. So it is a solid solution. So that's why it contains only one phase, that is austenite or gamma. And when we cool it below 727 degrees centigrade, we will get pearlite. So means all the austenite decomposes or transforms into pearlite. So that's why we get 100% pearlite here. That is a layer of alternate layers of cementite and ferrite. So this is the microstructure of pearlite. Alternate layers of ferrite and cementite phases. So the diffusion of carbon in pearlite. So how actually pearlite forms? As we know, initially at austenite region, that is at more than 727 for 0.8% carbon, it contains 100%. It contains 100% austenite. And when we cool below 727 degrees centigrade, it contains 100% pearlite. But how actually austenite transforms into pearlite? So that we will study in this particular slide. So what happens first of all over the austenite grain boundary? It is due to the diffusion of carbon, pearlite forms over the pearlite forms. So what happens here? So imagine that this is our austenite grain boundary. So this is our austenite grain boundary. And what happens? And what happens here? First of all, the cementite layer forms. So this gray color is the cementite. So why cementite forms? First, because austenite has good percentage of carbon, that is 2.04 percentage of carbon. So first cementite forms over austenite grain boundary. So this is our austenite grain boundary, and over this austenite grain boundary, the first gray color plate, you can see it here, layer, first cementite forms. So cementite is a hard and brittle phase, and it is an intermetallic compound, Fe3C. A fixed stoichiometric ratio, fixed chemical composition, 6.67% carbon. So what happens when cementite forms? It takes all the carbon from the austenite. So from both the sides, from both the plates of the cementite, so cementite absorbs the carbon from the surrounding austenite, because cementite is rich in carbon. So it takes all the carbon from the surrounding austenite. Now surrounding region just close to cementite, you can see adjacent region close to cementite is now poor in percentage of carbon, because all the carbon has taken by the cementite. The surrounding region just close to cementite is now poor in carbon percentage, and that favors the condition for the formation of ferrite, because we know only 0.025 percentage of carbon can be dissolved, that is of maximum percentage of carbon that can be dissolved in ferrite. And close to cementite region, we have only very small percentage or very negligible percentage of carbon present. So that condition is favored to form ferrite, and ferrite forms on both the sides of the cementite. You can see it here. So ferrite forms on both the sides of the cementite. So ferrite rejects excess amount of carbon because it takes only 0.025 percentage of carbon. It rejects excess amount of carbon. So again, close to ferrite, condition is favorable to form cementite. Again, cementite forms. So cementite takes all the carbon from the surrounding, just close to cementite layer. Again, condition is favorable to form low percentage carbon phase, that is ferrite. So again, ferrite forms. So like that, we have alternate layers of cementite, ferrite, cementite, ferrite, cementite, ferrite. And here in the formation of pearlite, so diffusion of carbon plays very important role, because every time so carbon diffuses into the cementite, the surrounding region is poor in carbon, so ferrite forms. So again, excess amount of carbon is diffuses out from the ferrite, so again cementite forms. So like that, so role of carbon in formation of pearlite is very important, and it plays very vital role. So diffusion, due to diffusion process, pearlite has formed. So controlling parameter in the formation of pearlite is diffusion rate of the carbon. If you control the diffusion rate of carbon, you can control the formation of pearlite, and it is a directly proportional relation. So diffusion rate of carbon to pearlite. If you control carbon diffusion rate, you can control formation of pearlitic phase. So this is the microstructure of the pearlitic phase, which shows alternate layers of cementite, ferrite, cementite, ferrite.